think we're about ready to start. And John, I'll turn it over to you for the demonstration.
Sounds good. Thanks, Dave. So for those of you that may have never been in one of our webinars before, it's largely going to be a monologue on my part, but there is a question panel inside of the webinar tool where you can ask any questions. Generally, I'll get to those at the end, and I can come back to any portion of the software and show you where that functionality is or answer any questions about that. Getting started, like Dave mentioned, we're going to be showing the SOLIDWORKS standard, professional, and premium plastics packages today, and give you an idea how to set up parts, run a flow analysis, run a pack analysis, and then get to the warp side of things as well. It is an add-in to SOLIDWORKS. What you'll end up having in your software is under Tools and Add-ins. You will see the SOLIDWORKS Plastics add-in here. It turns on and gets you another toolbar inside of the tools. And largely, you don't need to click on a lot of what's up here, but they're nice toggle switches and things inside of the software for various purposes. The majority of the plastics functionality is going to be found here in this tab that appears after you turn the add-in on. There's various areas in here to discuss, and you're going to see similarities between all three products. It's really just a matter of what level package you're at for the different analysis functionalities. You're going to need to mesh the model, and that can be done one of two ways. You can either do an automatic or a manual mesh of the model. Auto just goes through and gets a good clean mesh for a quick analysis. Manual is going to allow for you to refine the mesh in different areas. If you're particularly interested in how these ribs are on the side of a part, for example, you might want to refine the mesh more in that area than in others. You're going to set a polymer material and a mold material. So you can have a series of favorites here, but there's also an entire database of roughly 4,000, a little over 4,000 different plastics. They're grouped by family or by company that manufactures the plastic. And then in all levels of the software, you're going to be able to user define your own materials as well, so that you can lay out custom materials in the software as well. Keep in mind with regard to that, though, there's going to be a fairly large amount of data that needs to get input specifically for the viscosity of plastic, as it is temperature and shear rate dependent. This database is also searchable via this find icon here, and that will let you find a polymer that is available. And if you don't know the name of it, one of the really cool things within this database is you can find all the polymers within a given range of all these different criteria. So if you know the mold temp or the melt temp of the plastic that you're looking for, not necessarily anything else, you can go ahead and set those rates to be able to find that material as well. Each one of the types also has a generic, so if you're not necessarily interested in an exact chemical, you can just grab a generic and it takes an average of that ABS-like material, for example. The mold side of things as well has a database of all the different metals that you may be making a mold out of. And these are largely going to be used for the transfer of heat through that material for the means of getting you some cooling analysis on the software. With the standard package, you're going to be able to set the fill time. Here you see that it's grayed out. This is what the software is determining will be a good fill time for the part. It's roughly about a half a second on this. If you prefer to fill it slower or faster than what it's coming up with, you just simply clear the auto checkbox and then you can key in whatever you want. The melt temp it's getting from the plastic itself, but you can override that as well. And then you give it a start mold temperature, so say if you're preheating your mold, and the injection pressure limit of the machine. One thing to note here is that if the machine spikes in pressure higher than this number as it's running this test, it will short shoot the mold and stop the analysis there. Case in point, it will short shoot in that machine based on that analysis. You can also set some fiber orientations to that and co-injection for more structural plastics. You can even go as far as to set a mold temperature profile. So rather than just an ambient temp, you can say that the mold heats up and then cools off based on a PLC controller, for example. Once you set your fill settings, the only other thing that you need to do is set an injection location. So this looks at the mesh and it sets a specific point at which you're going to inject the plastic. This can be a series of faces. There's a number of different ways to set up the injection location. So they have what's called a node placement, where I just pick the point, it grabbed one of the triangles on the mesh and is going to pour plastic in at that point. You can also do something called a face gate, which is allowing me to pour plastic into a given series of faces along one edge of the model. Or you can do something called a control valve. And what a control valve is effectively doing is it allows you to do valves gate sequencing. So if you have multiple gates on the part that you open at different times, specifically to change the weld lines on the part, you can control the gate valves as well and when they open and close within the model. You set an overall diameter, and it will set that as well. Now, if you don't know where you want to inject your plastic from, there's also a button here that will get you up to 10 different suggested locations for all these different injectors. So if I say I want it to go find 2, it suggests that I inject here and here will get me the best results for 2 injection points as opposed to the one that I picked over to the left. In fact, if I go and clear these off, I find that it suggests that I shoot in the middle of the part here for the best injection on this part. Now, of course, that's going to get the best flow characteristics, but that doesn't mean you can actually fit that injection point into the tooling on the mold. So it's just giving you the best idea of where it thinks the fill is going to relate from that standpoint. I'll go ahead and cancel that so my injection point stays over here. And that's all the setup that needs to be done on a part to be able to get a run flow analysis. So you simply right-click on this and hit Run, and it will go and launch the solver and the software and be able to come back with live results. So as it fills, it sends live results to the screen in 10% increments. And the finished product ends up looking like this. So here's an example of some of the results that you can get with the standard package in the software. It shows an overall fill time, and of course I shot from the left side of the part, so what you're seeing in red on the screen right now is the longest time it takes to fill, i.e. the last thing to fill. There's an animation that you can play with that to show how the plastic flows into that cavity inside of the mold, which you can pause at any time to look for specific issues and areas within that. The other thing to note here is some of the check boxes in this case. So if I take a look at air trapping inside of the mold here, I turn that on. The purple spheres that have now showed up on the screen here are showing potential places where you would want to vent the mold. All the ribs have an air trap as plastic is flowing up into those. As the plastic flows around this area, we have an air trap. And then we get this because it's the last place to fill inside of the animation itself. And you can kind of see where the plastic's flowing, get an idea of these. But the purple spheres just give you a good, clear understanding of where gases may be trapped in the mold relative to the injection process. Some of these other options, I'll show you in some other examples where it makes more sense. Weld lines, for example, are really coming to play when you have multiple injection locations. The fiber orientation I didn't set any fibers for, but you can get an idea of the flow and the fiber orientation in the mold. And then the velocity at the vector, this is showing the flow of plastic, if you will, at the end of the filling process. So effectively the direction the molecules were moving when it got to end of fill at this point in the model. You can also take a look at the pressure at the end of fill, and this is generally a direct inverse of the fill time, right? So what you see in red on the fill is generally what you're going to see is the lowest pressure inside of the plastic mold, where the last thing to fill is going to be the low pressure. The first thing to fill is going to be the higher pressure area. You can see temperatures at end of fill, and one of the things that I found kind of interesting here is I'm seeing just a little bit of temperature spike at the injection point, but I'm seeing 50 degrees on this entire mold at the end of the filling process. And at first that didn't make a lot of sense to me until I clicked on this button here. And what this is doing is it's now showing a cross-section through that model. Because what's actually happening is right where that mold is touching the wall of the mold here, where the plastic is touching, that's going to immediately cool off due to the fact that the mold is at 50 degrees. But inside of this plastic is still very molten and non-crystallized, which is why we're seeing the 230-degree interior temperatures going on here. You can move these clipping planes to be able to see various areas throughout the model for your interest, see where you've got heat built up inside of the process. And exactly how hot things are at the end of fill are important, but even more so in our professional level package, you'll see at the end of the packing phase, they're even more important because that's when you're going to release the part from the mold. So we're looking for more uniform temperature cooling by the end of pack as well. There's some bulk temperature plots as well, and you can turn on and off these slices through the materials. This is giving you overall bulk rather than point-based temperature filling, showing you that I've still got quite a bit of hot material in through here. There's quite a bit of hot material at the end here as it injected. I'm getting some cooling off spots up in the corners and then this flat land here. And this is the flow front central temperature. So giving the idea of the actual flow front of the plastic as the temperature passes through the fill. And if at any time you're wondering exactly what these plots are showing, this little question mark right here will launch and show you all the results of all the different products, and you can just choose particular one and it will explain exactly what that process is showing, all the buttons that I'm showing you through, and explain with some graphs exactly what it's talking about within each one of those plots. There's a temperature growth at end of fill. So we're seeing potentially where the plastic may shrink or grow based on the pressures at the end of the filling operation there. You get some shear rates at the end of fill. And of course, we have a shear spike at the injection point, but there's also a little one at the tail end of the fill here as well. You're getting volumetric shrinkage at end of fill. So right here, we're seeing up to an 8% shrink rate at the end of fill. And again, looking at the packing phase is probably going to be more relevant to how much the part shrinks as it comes out of the mold. But what we're looking for here is a relatively uniform shrink rate across the part. And because I started on one end, I'm getting some non-uniformity on the other end of this part. The freezing time at end of fill plot that shows here is relevant because you want to make sure that you're not freezing near the gate location at the end of the filling operation. And what that signifies is the plastic has turned to solid material at the plotted place here and given time frame within the flow. So if I have any of this solidified specifically at the gate location, the packing phase is no longer exerting pressure on the plastic and not doing its job. So what we're looking to make sure is that we don't have any gate freeze at this point on a part like this. This gives me some overall cooling time as well, but I do want to make clear that this is not taking into account cooling lines in the mold. It's only taking into account an ambient temperature diffusion from the 50-degree material that we set for the mold wall itself. The premium level package that I'll show you a little bit later has the ability to put in cooling lines, temperature, flow rate through the water, etc., to get a more accurate result with regard to cooling. But this will give you an overall 5 seconds to cool a part down like this. Gives me the temperatures at the end of that cool phase, and you can see we went from 225 to 150 on this part. There's a sink mark analysis on this as well, and what I'd like to point out here in particular is I've made these ribs very thick with regard to the plastic material here, and anybody that's got experience in the injection mold plastics industry knows that's probably not a good idea. I did so on purpose here to showcase the sink mark analysis here. Now, in the professional and standard package, this isn't necessarily a depth, but more of a ratio of sink mark. In the premium level package, it will actually give you the depth of sink marks as well. But what I'd like to point out here is the non-uniform color that we have going on here. This very quickly transitions from a light blue to the green to the yellow in these areas, which is going to be problematic of sink mark on a part like this. Gate filling contribution, again, here I've only got one gate, so this is all going to be. The more gates you have, the more color codes it shows on the side of the screen over here to show you what portions of the gates did what work in the filling process. The ease of fill is a 3-color coded plot that shows you what areas on the mold were easy to fill, what was getting difficult, and what was nearly impossible to fill in the red zone here. Obviously, in this case, this is the last portion to get filled, so you're going to see a red spike there. But if we go back and look at the pressure at end of fill, we're pushing up to 92 MPa, and I said that the limit on this machine was 100 MPa. So we're nearly maxing out the press, specifically in this red area right here, trying to get that to fill. And more than likely, if we have any additional issues, this is where a short shot's going to occur. This again shows the frozen area at end of fill in a different plot graph. And again, we're trying to avoid any green areas near the injection location at the end of the filling operation. So that's the basics on the layout and the run through on the different plots for the flow analysis. There's a couple of different options to test variance in the software. So I could do a save as and make this a separate part, but one of the really important things about SOLIDWORKS is its configuration manager. Well, plastics plays into that as well. So if I jump over to the configuration manager here, I've got default, which has these thicker ribs. If I double click on the smaller ribs configuration, you can see the ribs have thinned out here now. It's now loading all the information for the plot that I've done relative to that configuration. And now I can access results of a thinner rib scenario part in a very quick fashion. I simply jump over here and take a look at the flow results. It loads those into memory. And then I'm getting the overall fill times, pressures at end of fill again here. One of the things I notice immediately is I've dropped MPa considerably by going down. And then taking a look at the sink mark analysis on this side, you can see I've got a much more uniform displacement in the sink mark analysis here. I've still got, potential marks going to happen here, but I'm more uniform across the board on all of these colors, which is going to give me a more uniform cooling effectively, which you can also see in the temperature at end of fill. A lot more uniform across the part. The ease of fill, much easier to deal with on a part like this as well. So those are the basics on the standard package. I'm going to open up some other files to show some of the professional level functionality as well. So here's another file that I ran, and it's loading all that information as well. This is showcasing one portion of the professional level package. So part of the professional level package is getting into the pack phase within a mold. And what this is doing here is this is showcasing the fill operation, and assuming that we don't have gate freeze at the end of fill, then the packing operation is continuing to put pressure on there to try to fill out any sink marks and potentially keep the plastic pushed against the edges of the mold while it's cooling to avoid any warpage and sink marks and material. The layout's exactly the same. You're simply able to also run a pack. So instead of just running the fill analysis, you'd run a flow and pack. You'd end up with both plots down here. So if I take a look at the pack results in this case, we see a pressure at the end of the packing phase, which is obviously much lower than the injection phase itself. We're just holding pressure on the mold at this point. We see a temperature at the end of pack. So we're still at a max on a part like this at 222 degrees at the end of the packing phase. Some overall bulk temperatures. And again, you can take a look at cross sections and things through the model, be able to see uniform cooling. The vast majority of what we're looking at on the end of pack is no longer in the red area. We're now down in the blue and yellow areas, green areas, 150 to 180 degree temperature range. You got shear stresses remaining in the part at the end of fill. So there's a max of about 40 MPa of stress on this part. The vast majority of it is down in the 0 to 8 MPa range. This plays into warping, but without necessarily going to the warping package, you can see some of the stresses and the shear rates of that stress within these plots. You have a volumetric shrinkage at the end of fill, at the end of pack rather in this case. So we looked at this at the end of the filling operation. On the last part here, we're looking at the end of pack. So this is prior to the part coming out of the mold. I've got a max of around 9% shrink rate. The vast majority of the parts more along the lines of a 5 to 4% shrink rate, which is pretty typical of an ABS type material. Temperature at post filling, so we're down to 175 after the cooling operation, what it suggested in the fill op. The freezing time, so this is the glass transition temperature of the plastic, is at about 11 seconds on a part like this. Show some of the residual stresses in the part after the cooling operation. And then the frozen area at the post-fill. So here, the opposite is the case relative to our filling operation. We basically want to make sure that nothing is frozen near the gate locations on a fill operation, but we're actually looking for the majority of the part to be frozen at the end of the packing operation. That way you're not knocking a part out of the mold that potentially still has liquid plastic inside of it, as you're going to have a lot of tolerancing issues, deformity, cooling problems, things like that. So what we're seeing here is now all the green is properly cooled. We've got very small areas throughout the mold that may still be molten, which is a good time to release this part out of the mold and cycle the next component in. All levels of the product are also capable of kicking out a summary and report. So all you have to do is double click on this. It gives you some overalls on the type of plastic, the melt temps, its overall size. From a pack standpoint, shows the max stresses and shear rates. When you hit the green check, this will allow to set up a template for the report generation, where you can put in title, date, department, an overall introduction and any special notes that you want to say about it, and then particularly what you want to capture into these files. So the different screenshots of all the plots, things like that. Here I did a results and a pack plot. You can hit select all to grab all of these. When you click on the OK button, it will launch and take screenshots of all of these relative to the position of the model on the screen, and then it will kick out an overall Word doc and a PowerPoint that has slides and pages in the Word doc with all the information about this in effectively one button click. Here's an example of the one on the cam body that I showed earlier. So roll this back up here. Gives you a shot of the plastic part. Here's the title and things. Gives you overall contents on the part. Get the overall size of the plastic part, the material and all the specs on the material, all the specs on the flow and the cooling side of things. Particularly the clamping tonnage force is plotted here as well. Back in the software, you're able to get to that as well. Right here is an XY plot, and that will launch the clamping tonnage that it takes to hold a part like this. So this is showing a graph of the max inlet pressure on a part like this. We're spiking somewhere around 20 MPa, 18 to 20 MPa on this part before the pack phase starts. But that's not necessarily the clamping tonnage, that's the max injection pressure of the machine. You'll need to look at the XYZ coordinate system. In this case, I'm looking to clamp this along Z is how this is going to close. So if I take a look at the clamping tonnage around Z, I'm at about 16. So, safely throwing this into a 20-ton press would inject a single one of these parts at a time. And the plot can show you that. You can also do nodal pressures and node temperature plots, where you're picking spots on the plastic part and showing those over a time graph with regard to pressure or temperature. The rest of this is relative to what package you have. Obviously, I showed you a standard report, so I'm only seeing flow results. With the professional level package, you'll get into the pack stuff. With the premium level package, you'll get into the cooling and the warp results. Any special notes, one of the things that I had suggested was to thin down the ribs to avoid sink marks. And you can see down the stream in this report, the plot kick out here, showing the non-uniform cooling around those thicker ribs. And I showed earlier the graph of this being much more uniform with regard to the sink marks and the thinner ribs. Got vectors, ease of fill, things like that. So between the two, very easily go back to the camera, kick out another report on the thinner ribs, and we can showcase between the two parts as well. In addition to the packing side of things, another functionality inside the professional level package of the software is the ability to handle a runner system. So some of the documentation that you may see about this product shows that you can't necessarily do a multi-cavity mold with the standard level package. Well, that's not 100% the case. What I would say is that you can't do a multi-cavity mold efficiently. And the reason that I mention that is because you could absolutely model each one of these parts, and then you could model the runner system yourself into the software and then inject about the sprue and see what happens. And the standard level package of the software can do that. Where the professional level package comes into play is that A, you don't have to, and B, it can balance that runner system afterwards. So when I take a look at this, it does like a beam element here as it lays out these runner lines, which is done here in what's called channel design. So you'll select just a grid work of what you want the channels to overall be, and generally your sprue bushing is going to be larger than the runner system, and then they're going to taper down as they go to inject into the part. So this is the actual interface with the plastic wall, but the sprue bushing itself is pushing plastic in here, and then this is going to end up being removed and wasted material. It does have the ability to do a hot or a cold runner system. The wasted material is obviously part of the cold runner system. The hot runner system, you're setting temperatures to this to keep this area as molten plastic as you cut off and drop parts out of the mold. So you set this to be a runner. You set the overall diameters here. And the easy way to do a taper is you effectively choose this line, and then you're just setting a start diameter and an end diameter, and it takes care of the trigonometry that it takes to be able to taper that down for you. You can set the number of elements to the runner system as well. So it quickly and easily will lay out multi-runner systems. And in this case, I'm particularly showing a family mold. And the reason that this is important is because if you had two of the same parts and you inject at the same point, you're going to have a nice uniform pressure across both parts. This is not necessarily the case on a family mold. If my goal is to shoot both of these in the same block of steel, I may get this one filling up before this one, or vice versa. And that can be problematic because now you're pressure spiking on one of the sprues and not necessarily sending the right pressure over to this one, so you can have a short shot on this part while still making this part correctly. So the other huge functionality that the professional level package brings to the table is that you can do something called runner balancing. So I initially set these channels to be 10 millimeters in diameter and then 5 millimeters in diameter and tapered down. Then I went back and ran a runner balancing on this, which is literally just launching this, telling it the max, the min, and the inlet size. You hit the green check or hit the start button and let it run, and it will automatically go through the software, figure out that this one was filling first, and then it downsizes the runner relative to the sprue, and you can see a smaller diameter here than here, to get these to fill at the exact same time to avoid that pressure spike that happens between parts on a family mold. As you can probably imagine, figuring these numbers out yourself can be pretty problematic. I've talked to a lot of companies that are literally just out there with a die grinder opening things up until they get it right. And actually modifying the tools in the press or pulling them back out to do the modifications. So if you can get this runner balance set ahead of time, you can have something a lot closer to a production run tool up front in the design process before even designing the tooling side of this. Gives you an idea of the different layouts of runners. You can test different ideas, balance all the runner systems, and be able to come back with a viable multi-cavity tool layout prior to committing to the overall tooling cost, which, as I'm sure you're aware, is quite expensive. Lastly, I'd like to show you some of the premium level software functionality. And here I've got a plastic part. This top of a smoke alarm component. So there's some sketches laid out, in this case not for the sprue and runner system, but for the cooling line analysis. The first thing that I'm going to show, though, is what happens when we run this with an ambient temperature. So what's loading into the computer now is the flow, pack, and warp function that has been run here. And there's some warp settings that you can deal with as well, the overall ambient temperatures and gravity. But for the most part, warp is the residual stresses left in this part from the injection process at the end of the packing phase. So if we take a look at the overall warp results on this, it comes back and shows a total X, Y, and Z direction of warp with its total stress and the deformation scale. It defaults, I believe, to 10, really showing some nasty distortion in the part. Personally, I like to go back to a 1 so I can take a look. And what you'll see is you've got the wireframe model being the theoretical perfect, and then the color-coded model here being the warp that occurred within this part. So if I'm interested in looking at this as a breakdown of X, Y, and Z here, I can click on this button and it shows that I'm pulling in on this side roughly 0.5 millimeter. The Y direction, it's more of this corner pulling up about 700 thousandths of a millimeter, 7.7 millimeters. And then in the Z direction here, I've got this drawing in roughly 0.4 of a millimeter here. The overall total being this moved around 0.9 worst in this upper corner here. And again, exaggerating that, you can see this is actually pulling down here. We've got the part warping up in this corner. So, something to take note of is if this is meant to snap to another component and you're trying to hold tolerance across the bottom there, we potentially have some warpage issues with regard to flatness on a part like this. But again, I'm showing exaggerated here at a 1-to-1. That's much closer to flat. Still not perfectly flat, which we can see. And we had a movement of about 0.9 millimeters. So we're talking almost 40 thou, 35 thousandths of an inch movement. So it depends on which tolerance ranges are and things like that. There's a sink mark profiling as well here, and this is just a checkbox that's also showing you a similar plot to what you saw in the flow package, but the number here is actual sink mark deformation after the packing phase. So I can expect to see very small sink mark here and here on the part. We're talking 0.02 millimeters, so we should be in pretty good shape on a part like this. If we saw this at 0.5 mil, I'd be a lot more concerned about the Class A surface, the customer-facing surface of this having a sink deformation in it. And you can actually animate that deformation as well in the software. So the warping package in this case is taking into account only the overall ambient temp of the mold, similar to the first two packages that I showed. In this other configuration, they've taken into account the cooling lines as well. So here, I'll load up and you'll see the same analysis run, only this time they've run a couple of different cooling line sets. I'm going to jump over and show you those and how they're set up. There is a material database on coolants, so you can effectively run water or different glycol and water combinations, effectively coolant, right, that you can specify inside of here. And then you set up the cooling pipes like this. So similar to the layout of the runner design, you're using, again, just a center line here, connecting the dots. It does beam elements again. But you're specifying what the inlet and outlet is. So here, this top is showing the coolant flow in here and then back out this direction. There's one that flows through the middle this way. There's another one that flows in this way and back out. On the bottom, that's not the case. It's a very similar layout, but there's only one inlet, and it travels back and forth to one outlet. This is actually a very common mistake done in molds where you're passing this through. And the reason that this doesn't work well in a lot of cases is that you're putting cold water in here, it's getting hot by here, and now it's not doing as an efficient job transferring that heat out of the mold the rest of the way through this because it's already been heated up before it exits and more cold water is flowing through. So uniformly cooling the top portion of this is going to be a lot better solution. Now I've got a quick heat displacement passing through the middle and even heat displacements passing through either side. And all of those are set up through the individual pipes that you select over here. You can set the inlet temperature and the flow rates to each one of these and exactly what coolant's being run through each one of the lines if you want to. By taking into account all the cooling setup as well in this, we'll see the cool results and the warp results. So here it shows the overall cooling. Gives me an overall part cooling time. So this is now completely accurate to real life condition. I've got the ambient temperature of the mold, the material of the mold in play without even having it designed, the overall layout of the cooling lines and how they affect it with the temperatures and flow rates of all the water. Gives me a cycle average temp of the mold. So this is after I'm cycling it, how hot does the mold stay before the next part shoots in. The temp of the part at the end of cooling, we're down to about 137 degrees in this case. Cycle average part temperature, the part temp at end of cooling, the mold temperature at the mold temp at end of cooling, and then the overall heat flux relative to the exchange. So obviously the bottom of this is getting warmer than the top of these rather than the bottom of those. And then the heat cycle load, similar in this case, getting the most temperature spike going on in here where it's coming down in contact with the plastic or very close to the plastic inside the mold. The warpage on this side is now also taking into account those temperatures. So when I come back and look here, we actually see that this warped more when we put in cooling lines. And the reason for this is we're now sucking away heat in different areas as opposed to assuming an ambient temperature. So we have a much more realistic representation of the mold. So now we're seeing a little bit more warpage in the total direction. In the X, I'm seeing about 0.8. In the Y, I'm seeing about 0.6 now. And in the Z, I'm seeing about 0.7. The overall total, we still have the same corner pulling up, but it's pulling up a little bit more than I had originally found. And just giving a much more accurate representation of the cycle time on this part and something that we can take into account with regard to the actual warpage on the product now that we've keyed in all the different factors that are potentially possible, possibly affecting the overall warp of this part after it has been filled, packed, cooled, and released from the mold. So hopefully that gave everybody a good overview of the different products and what the capabilities are. As David mentioned, he's going to be following up with you guys with the product matrix so you can see exactly what's in what packages. But in the meantime, if you have any questions, please key them in now. I'm going to take a look at the question area, see if anybody's asked any yet, and feel free to add any for the time being as well.
Yeah, while you're adding your asking the questions here, I just want to reinforce again the three levels of the product are really designed to help you get better parts in less time. Hopefully that helps the bottom line of each of your companies. Reduce the number of molds and actually the time it takes to build these molds because you know a little bit about parts up front and how they're going to operate in the mold, and less time in setting up your tooling and really the whole shake out there when you go to originally make the parts. Hopefully the more you understand about this up front, you can reduce the time to do that and saving time also basically get to the bottom line of saving money. Do we have any questions here?
I do see one from Raphael asked, could all these temperature profiles be estimated for 3D printing as well? Let's see. I suppose that it's possible. However, I'm assuming that the 3D printing side of the question here is related to an FDM process, and the FDM potentially having a warp to it when you do a 3D print. And I'm assuming FDM because the other processes don't really get very hot. This is going to give you temp profiles on the injection shot of the plastic. So I don't know that we're going to see the exact temperature profile you would see in an FDM process per se. I'd probably have to do a little more homework into that, see if that's a viable option at this point. Anybody else have any other questions?
Sounds like you're pretty thorough.
Great. All right, well, we'll be glad to follow up with all of you if you're interested. And I believe I see a name in there and we're actually demoing with next week. So look forward to letting you guys know anything else you need to know about the plastics package, and let us know if you've got any other questions. Thank you very much for your time.
Thanks all. Bye now.